Stupid. I didn't turn in my volleyball senior night thing.
So we've talked about the nucleus, protons, neutrons. We talked a little bit about electrons. This unit is all about the electrons. And they're pretty cool. They do some really neat stuff that affect our daily life quite a lot. This big, long string of numbers is called an electron configuration. And it's kind of like an address. And by the end of tomorrow, or maybe the next week, if you see a string of these numbers, you'll know exactly what element this represents. And if I say, what's the electron configuration for whatever element, you'll know exactly how to write the electron configuration based on where it is in the periodic table. So there's some neat stuff in here. One of the things, pretty much what we're going to talk about today is something called atomic absorption and atomic emissions. So this represents an electron zooming around the nucleus. And you'll notice when a wave comes in, it jumps up. And then when it jumps back down, the wave goes out again. Okay? That's called atomic absorption and atomic emissions. So it's kind of like this. Actually, I got to read a book first. First, we have to have story time, and then I will continue. So I've got to have story time. If you can't see the illustrations, let me know. So we're going to be reading Quantum Physics for Babies. And again, if you can't see the instructions, just let me know. Are you ready? Yeah. Okay. Sorry, I don't have little cots for you to sit on, but here we are. Okay. Yeah. This is a ball. This ball has energy. This is a ball. This ball has 0 energy. All balls are made of atoms. There are neutrons and protons and electrons. Electrons have energy. This electron has the most energy. This electron has the least energy. Energy is quantized. An electron can be here, or here, or here, but not here. Or here. There are no electrons with 0 energy. An electron can take energy to jump up and must give energy to fall down. This amount of energy is a quantum. Now you are quantum physicists. Done. This book is 10 years old. I love it. Okay, so let's talk about what's going on here. We got our neutrons, protons, and electrons. So we got our neutrons chilling out in the nucleus. I'm just going to use one. There's our neutron. And we got our proton in the nucleus. I'm just going to use one. There's our proton. And then previously, before about 120 years ago, it was generally thought that the electrons were in a big cloud around the atom. First, they were in a ball, a solid ball. Then they were in a cloud. And then this guy named Niels Bohr came along. And I'll show you his picture in a little bit. And he said, I think I know what's going on. I think electrons are in levels. So electrons are found in levels. And there's 7 or 8 of them, according to the technology that we currently have. So let's put an electron right there. This is an electron. And specifically, this is just the hydrogen atom, hydrogen 2, single electron. And this electron's at its lowest energy state, so we call it the ground state. Ground state. Oh, yeah, thanks. Okay, so It's at the lowest state, just like you and I are at the lowest state, so we're going to call it the ground, the lowest energy of the electron. You know who this is going to? Or? Right. What is this? Oh! That's what that is. Okay, anyway, so back to work. So electrons here at the ground state. And what Niels Bohr did is he started hitting an atom with energy. He gave it a little bit of energy, not much happened. So he gave it 1 unit of energy, nothing happened. Then he gave it 2 units of energy, and nothing happened. Gave it 3 units of energy, nothing. But then when he gave it 4 units of energy, the electron jumped up 1 level. And when something jumps up to a higher level than it would normally be, we call it excited. So the electron is now excited. And it did that when it went from 0 to 4. So adding plus 4 units of energy kicked the electron up to level 2. Yes?
Actually, never mind.
Okay. So again, we can theoretically, we can call this level 0, 1, 2, 3, and so far, or we can call it 1, 2, 3, 4. But it jumped up a level. Now this is what was interesting. Electrons don't stay excited for very long. They pretty much immediately fall back down to their ground state. -4. So far, so good? So this is interesting. It's like, okay, so if I give it 4, if I give it 3, nothing happens. If I give it 4, it jumps up 1. And then when I give it 5, guess what happened? It still jumped up to level 1. And you gave it 6, still jumped up to level 1. And 7, still to 1. 8, still jumped to level 1. 9, it still jumped to level 1. When you gave it 10 units of energy, that electron jumped 2 levels. So now the electron's up here, and it's still excited. It's just more excited when it took in 10 units of energy. And then something kind of interesting happened. An electron that is up here, 2 levels high, can fall down once, and then again, it can fall down in 2 levels, where it would lose 6 and lose 4, or it can just fall down back to its original ground state and lose 10. So far, so good? So the energy that an electron will take is quantized, which means it is a very specific amount. In fact, the smallest packet of energy that can exist in the universe is called a Planck, named after this guy named Maxwell Planck. German dude, I think. So the amount of energy was quantized. If you gave it 3, nothing would happen. If you gave it 4, it would jump up 1. If you gave it 5, it would still jump up 1. Because electrons can't be in between the levels. They have to be at individual levels. Make sense? Okay, if you're with me so far, a question?
If you gave it 18, would it go 4? Is that the pattern?
Maybe. It is. There's no set, like, it's, I can see like 4, 6, 8. There's no set pattern, but it would probably jump it up to another level, yes. Okay. Now, how did he know that the things were jumping? Well, when energy goes into an atom, it immediately comes back out. And if you were to look at the light that comes out of an atom, kind of like the LEDs that are on the ceiling, electrical energy is going in and light energy is coming out. Well, when this electron here jumped back 4 units, it gave off a red light. A red light that was carrying 4 units of energy. And then when this electron up here, that was 2 levels up, when it fell 1 level, that drop of 1 level gave off a green light. Okay, well anyway, carrying 6 units of energy. And if it fell 2 levels, dropping all 10 units of energy, that gave off a blue light, carrying all 10 units of energy. So it turns out that electromagnetic radiation that we can see, light, all these beams, all these bits of energy are electromagnetic radiation. And they are specifically called photons. A photon is a single quantum of light. So these are photons. We have red photons, we have green photons, and we have blue photons. An electron that undergoes a transition from high to low, low to high, when it goes from a higher level to a lower level, that transition will release a photon. A photon is a tiny packet of energy. It is a quantum of light. Anybody knows where my clicker went? I set it down somewhere and I totally forgot where I left it. Oh well. Okay. So, Bohr's model was like this. We have electrons. They were previously in this big, messy cloud. And he said, what if we put them in shells? So, sorry about the animation. It's all mixed up because of Google Slides, the transition between PowerPoint. Electrons at the ground state. It absorbs energy and gets kicked into the excited state. But it doesn't spend very much time there. In fact, it basically returns instantaneously because electrons are energy. Time doesn't exist for them. So they go up and come down pretty much instantaneously. So they come back to their ground state and they release the energy that they absorbed. And the cool thing about quantum is if an electron absorbs 8, it releases 8. If an electron absorbs 100, it releases 100. Which is why LEDs are so much more efficient than old incandescent, those little metal filament light bulbs. Because those metal filament light bulbs, they had to heat up and release and create a lot of heat. So if 100 units of energy went in, 90 units of heat came out, only 10 units of light. With an LED, if 100 units go in, if the electronics were perfect, 100 units would come out. But as it is, you got to use a little bit of energy to get the electronics to work. But they function at the quantum level. So ideally, you could have a perfectly efficient light bulb, 100 in, 100 out. In reality, you lose a little bit of energy to make the electronics work, but for the most part, at the quantum level, whatever goes in, comes out. Make sense so far? All right. If you have any questions, wave your hand around. If you're ready to move forward, give me a thumbs up. Okay. Let's get some more lingo. I'm sure it's going to show up like, oh, it's there the whole time. Okay, so the word we use for absorbing energy is just atomic absorption. Atomic absorption happens when an electron jumps up to a higher level by absorbing some kind of energy. Get to its excited state. That's atomic absorption. It just bananas. It just disappeared partway through the third period. Where did it go? I'm sure I just set it down during I was just lecturing like I was now. I'm sure I set it down somewhere, just no idea where I put it. Oh well. Found it. It was on the force plate. Okay, so atomic absorption is when an electron gains energy and jumps up. And then atomic emission is the opposite of absorption. Atomic emission is when an atom releases the energy and jumps back down, falls back down to its ground state. And here's the cool thing. All of what we consider light is electromagnetic radiation. That's what we call it, EM, electromagnetic radiation. Because it's electrons that are coming from electric and magnetic fields. That table, which I'm going to show you up here too, has a list of the common types of electromagnetic spectrum, or electromagnetic energy. It's a spectrum, meaning it goes from high to low or low to high. In this case, it goes from low energy on the left side to high energy on the right side. You can see at the bottom where it says energy of 1 photon in electron volts. Don't worry about the unit. An electron volt is just a unit of energy. Don't worry about that. No, what's an electron volt? I'll tell you later if you're interested. Right now, just realize it's energy. So we have all these photons. They're all light, but we can't see them all. We can only see this tiny slice that we call the visible spectrum. But radio waves, they're light. The radio waves coming out of your cell phone, they're light. Your cell phone is just a radio transmitter and receiver. It's just sending radio signals back and forth between a tower and your phone. But they're moving really fast. Microwaves, light. Infrared is an area of the electromagnetic spectrum that we can't see because it's lower than what we can see. We can see the visible spectrum. And even inside the visible spectrum, we can make some conclusions about the energy of photons. We have a red photon that was released when the electron dropped 4 units. We have a green photon that was released when the electron dropped 6 units. And we have a blue photon that was released when the electron dropped 10 units. So which of these colored photons, red, green, or blue, is carrying the most energy? Blue. Yeah. And there's 2 parts of a wave. There's the wavelength, how long the wave is, and the frequency, how many bumps the wave has. So, and all this information is going to come up here in a second. Okay. So, blue photons, higher in energy than red photons. And it works across the pattern too. Infrared photons are lower in energy per photon than visible light. Above visible light, we have ultraviolet, then the X-rays, and the gamma rays. Ultraviolet photons carry more energy per photon than visible light photons. So you got red, small, infrared, even less than red, which is what it means, less than red, less energy than red. And you have violet, high energy visible light, and ultraviolet are photons that have even more energy than violet.
Hi.
Hi.
I just have to ask 2 students their names for the yearbook. It's
Okay.
you guys over here. I just need your name for the yearbook to tag you. Yeah.
Us too.
Yeah.
Addison and Harmony.
Okay. And
Your
then
last name too.
yeah.
Hillier and Cook.
Okay, thank you.
Moving on. So, if you energize a sample of gas, you will basically release energy. But also the really cool thing is, if you send energy through a sample of gas, it will suck up some energy. Because that's what absorption is. It's sucking up the energy. And this is called an absorption spectrum. If you shine white light through certain materials, it'll selectively remove little bits of energy based upon what the electrons can use. So down here, you have an electron that jumps a little bit. Up here, you have an electron that jumps a lot. Maybe level 1 to level 8. Okay. Maybe here, level 1 to level 4, level 3 to level 6. But that's called an absorption spectrum. What you see when atoms absorb energy. And of course, the opposite is called an emission spectrum. This is what happens if you just energize some gas. It will release certain bits of energy. That's what we're going to do today. That's what I'm going to do today. Gas still on? Let's see. You've all seen fireworks, right? So do you know why certain fireworks are green or red or blue or white? It's because of the material that they set on fire. So there's an explosion and it releases a lot of heat. And then a lot of that heat gets absorbed into various metals. Metals are good at getting rid of their electrons. And then those metals, those electrons jump up and then come back down and they give off visible light. This is a solution of strontium. And if I spray the strontium into the flame, you might start noticing a color form. colors do you see? Yeah, red and orange. So strontium, when you energize their electrons, they release a lot of bands down here that you can see. There might be other things, but definitely the prominent color is the red and the orange. So would you say that the transitions in strontium are high energy or low energy? Low energy, right? This is a solution of copper. What colors do you see when copper gets energized?
Green.
Yeah, the greenish yellow. So would you say that the transitions in copper are higher or lower than those in strontium?
Higher.
Yeah, they're higher because each photon is giving off a visible light that is greenish, and green light has more energy. Make sense?
Yes.
If you're with me so far, give me a thumbs up. If you have any questions at all, wave your hand around.
What color does like oxygen? Is that why?
Blue.
Is that why the flame is blue when it gets hotter and more orange when it's not as hot?
Yes. In fact, if you, we actually have gas tubes somewhere in the department where you can run high voltage through gases. Yeah, oxygen is blue. Nitrogen is purple. Guess what color lightning is?
Purple.
Yeah, purple blue, exactly. Because lightning travels through the oxygen and the nitrogen in the air. 21% of our atmosphere is oxygen, 78% of air is nitrogen. So the lightning that goes through, it looks white, but it's actually bluish purple. That's going to be a common theme. Moving on. Buttons. I love my buttons. Buttons. Okay. Because of this, because of the beams of little bits of light, because each atom has a different number of electrons in different places the electrons could jump, they actually create a quantum fingerprint. Now, this is the simplest there is. This is just hydrogen. But they get more complicated. This is sodium. There's like dozens of transitions. This is mercury. Again, hundreds of transitions. Sodium lights used to be used in streetlights. Some older streetlights, you can still see them, they're kind of yellowish. So sodium lights are still used in streetlights, and mercury lights are still used out there on top of the football field. They used to be used in gymnasiums, but we're like, no, we shouldn't have these things inside. But they still use them in football fields because they have all these colors of light. And if you have all these colors of light, they mix up in our eyes and they look what color?
White.
White. So sodium looks kind of a yellowish white, and mercury looks kind of like a bluish greenish white, but it looks more or less white. And they're pretty efficient because, again, they're functioning at the quantum level. And again, you can look there's dozens of them, you can search for them. In 2018, somebody asked me, what causes the aurora borealis? This is kind of neat, the northern lights, aurora borealis. What happens is charged particles from the sun get ejected towards our planet, and then they skip off our atmosphere. We have something called a magnetosphere. It's like this spinning Earth creates literally a force field. It literally is like the spinning Earth creates a magnetic force field that causes particles to kind of skip off our atmosphere. But the ones that make it just slightly inside the atmosphere, as they skip, they release energy, and then gases in our atmosphere absorb that energy and glow. And that's where the northern lights comes from. So the magnetosphere basically causes them directed bouncing through our atmosphere, and then that excites oxygen and nitrogen and argon and carbon dioxide, and all of those gases glow, and it lights up the atmosphere, which is pretty neat. Anyway, there you go. Questions? Okay, cool. Okay, so this is an identical copy of that poster over there. Now I should mention, that poster and this goes from low energy on the left to high energy on the right. Those two posters go from high energy on the left to low energy on the right. You know this because those posters have violet on the left and red on the right, and those posters have red on the left and violet on the right. So you just should understand that. Okay, first of all, good news. You don't have to do math with this anymore. You no longer have to do any kind of these math formulas. but you do need to know the relationships they represent. Let me give you an example. If you have a wave, remember a photon is electric, a little beam of light, it's a wave. So if you have a wave, there's a couple things you can tell about this wave. One is the wavelength, the distance from peak to peak of that wave. And you might notice that the red light has a very large wavelength. How does the blue light's wavelength compare? It's much smaller. Okay, much smaller. So the blue light has a smaller wavelength than the red light. Okay, so far so good? Now here's the really cool thing about electromagnetic radiation. It all moves at the speed of light. 3 times 10 to the 8th meters per second. Do I need to know that? No, speed of light. We call it speed of light. We used to use math, we don't use math in this unit anymore. So 3 times 10 to the 8th meters per second, all light from low energy radio waves to high energy ultraviolet all travels at the same speed. And because it all travels at the same speed, if you have a longer wavelength, then you have a smaller frequency. Frequency is how often you see a peak. So if your wavelength is really long, you don't see as many peaks, you have a very small frequency. So the red light would have a very small frequency. What would you say about the frequency of blue light?
It's more.
Much higher, because in any given space, you see a lot more bumps. So the frequency of blue light is higher than the frequency of red light. But the product of these two will always be exactly the same. It will always be the speed of light. So wavelength times frequency is always the speed of light. If your wavelength is higher, your frequency is lower. If your wavelength is smaller, your frequency is higher. That's super important. Definitely one of the things you want to write down. Because this is a constant. If one variable increases, the other variable has to decrease. Next. Energy of a photon follows frequency. So this is the energy of the photon. That's Planck's constant, that German guy I mentioned earlier. It's just a number. It's just a number. But the important thing is energy varies proportionally with frequency. If you have a higher frequency, you have a higher energy. Blue light has a higher frequency than green light, so a blue photon is carrying more energy than a green photon. How are we doing?
Good.
Questions? Okay, so those are the relationships you need to know, and they are testing. Again, I spent the last couple of days pulling all the math out, but replacing it with relationships. So rather than saying, this photon has a wavelength of this number, what's its frequency? Calculate it. Now it's, this photon has a high frequency. Would you predict its wavelength to be higher, lower, equal to the other one? Relationships, more important than math. Okay, here's what I've been talking about. All electromagnetic waves move through the same space at the same speed. Speed is wavelength times frequency. Wavelength and frequency vary inversely. In other words, high frequency, low wavelength, high wavelength, low frequency. Energy varies with frequency. And I stole this animation about 10 years ago because it's awesome. So look at the red photon. He's dancing. Is he moving pretty fast or pretty slow?
Slow.
He's moving the exact same speed as all the rest of them. But each of his jumps has a lot less energy. Whereas this little blue guy, he's moving the same speed, but he has to jump a lot more with a higher frequency to get going and keep up with his buddies. I love this animation. All right, if you're with me so far, give me a thumbs up. If you have any questions, wave your hand around. Yes. No, we're good. We're good. All right.
Wait,
Last thing. Yes, go ahead.
the upside down Y just means frequent or wavelength, right?
By the way, that upside down Y is called lambda. It's Greek. Lamb, like duh. Lambda. Yeah. Lambda. Lambda. So it's a Greek letter. Okay. Other questions? Okay. Last concept for today, and I love this. And I wish it didn't all come up at once, but again, I haven't. When I converted all my PowerPoints over to Google Slides, the animation gets all wonky. So it's very hard to get it to work properly. Okay. So the photoelectric effect is something that Einstein actually got his Nobel Prize for. First one? Probably the first one. And it works like this. It's really neat. So it turns out, if you have certain materials and you shine light on them, those materials will eject an electron. Then you can take that ejected electron, run it through a wire and a tiny computer, and then you can do math on that computer. I don't have any more solar-powered calculators. I gave them all away. I think I gave them to Ms. Murphy. But that's how a solar-powered calculator works. There's a little solar cell, and it absorbs visible light. Light comes in, energizes the material, and instead of light coming out, electrons come out. And those electrons have a special name. They are called photoelectrons. So a photon goes in, hits the metal. If the photon has enough energy, it will eject an electron. And because we like to name things special, an electron that gets produced through this process is called a photoelectron, because it's produced by the photoelectric effect, like these guys. These guys have these materials, and light comes in, the material gets energized, and instead of releasing the light like a mirror, that's what a mirror does. You know, a mirror absorbs light and then re-emits it. Nothing ever gets reflected in this world. It's all absorption and re-emission. Surprise! You want to know? Ask Google, ask YouTube, they'll explain it. Why things get inverted. It's because light gets absorbed and then re-emitted. Anyway, in this case, it's not a mirror. The light's going to get absorbed, and then it's going to get re-emitted, but in the form, the energy is going to get re-emitted, but in the form of an electron. That's the photoelectric effect. That's why my car hasn't touched the grid since March. Because I have a bunch of these guys in my backyard. And they just constantly absorb light energy and produce electrical energy. And then electrical energy is turned into chemical energy for storage, because storing things in the chemical process is really good. Okay, there's a couple things you need to know about the photoelectric effect. First, the photons have to have enough energy to overcome what we call the work function. You're not going to be tested on what the work function is. Just know that that's the amount of energy that the metal requires. So anything over that, you're going to kick out an electron. If I shine red light on these panels, nothing happens. It doesn't respond. There's not enough energy to cause the electron transitions to release an electron. If I hit it with green light, it'll release photons. If I hit it with blue light, you think it'll release photons?
Yes.
Yes, because blue photons carry more energy than green photons. So once you get enough energy to overcome the metal, then every photon you hit it with will release a photoelectron. Yes?
What would the sun be?
We'll talk about that. Don't let me forget to talk about that. We'll talk about what's called black body, white body radiation. Yeah.
Why does like the green one, and it ejects 3 electrons, but also the blue one also ejects 3 electrons, but the blue one's like higher.
Awesome. Because exactly that. Because the blue photons are carrying more energy, they eject more energetic photoelectrons. So it's still a 1-to-1 ratio. 1 photon comes in, 1 photoelectron gets kicked out. But the higher the energy photon, the higher energy photoelectron gets ejected. So again, if we were to shine red light on this, no matter how bright it was, the brightest red light, nothing's going to happen. But if we just shine a dim blue light on it, we're going to get some photoelectrons ejected. And then if we turn up the intensity, we'll get the same photoelectrons, but a whole bunch more. So intensity is how many photons you blast it with. More intensity, more number of photons. Higher energy, more number of electrons. Higher energy photon or electrons. Yeah.
So red light doesn't help solar panels, like you can't get energy out of it?
Correct. Yeah, with modern technology, they start at about green. But as I'm about to address with Chase, the sun produces everything. Okay, so in summary, before I talk about the sun, higher frequency means higher energy photoelectrons get ejected. It's still a 1-to-1. Higher wavelength, that means a lower energy photon might not overcome the metal. And then more photons per second means more photoelectrons per second. So if you shine a light on a solar cell that doesn't eject any photons, it doesn't matter how bright it's going to be, there's simply not enough energy per photon. All right. Those are all test questions, by the way. Again, I took out there used to be some really bad math, like kind of math. The math is gone. All you need to know is relationships now. Okay. Any questions before I talk about the sun? Okay. This is definitely a lean on the desk kind of discussion. What color is our sun? Orangish yellow?
White. Yours should be white.
White.
Yes.
It's white. If you look at any of the pictures of astronauts orbiting the Earth or in the International Space Station, or any of the satellites that got launched out and then turned around, the sun is white. And it's white because it releases all of the electromagnetic spectrum. All of it. Well, there's a limit. There's certain energies that are just like super high energy that sun can't produce. But for the most part, everything up there gets ejected by the sun. And what happens when you have all colors mixed together? White. The sun is white. Why does it look yellow up there?
Atmosphere takes up some of the.
Very nice. You were educated well in freshman, middle school?
8th grade.
8th grade? Yeah. All right. So yeah, exactly right. So white light comes in, and those who do art know there's something called complementary colors.
Yeah.
If you take the blue out of white, you get yellow. And the reason the atmosphere looks blue is the particles in the air bounce the blue light around and let the yellow come down. So the sun looks to be yellow because the blue got scattered. If you are on Mars, in fact, take a look at some of the pictures from the rovers on Mars. Totally bright day. You can see the shadow. You can see the shadow of the rover. It's like 2 o'clock, the equivalent of 2 o'clock on Mars. When you look at the horizon is just black because there's no light. There's no atmosphere to cause the light to get refracted around. Same thing would happen if we colonized Mars. If we colonized Mars. Bright summer day, it's going to have a bright sun above us, and then we look at the horizon, it's going to be black. The whole horizon will be black. Okay. If you're comfortable with what I just said, give me a thumbs up. If any part of this is unclear, wave your hand around. Now there's the next thing. Because I care about you, and I want you to win bets in bars, what color is almost every star? White. Yep, it's white. Now, certain stars have various sized peaks where they have an emphasis of various colors. Like really low energy stars will be reddish white, and high energy stars will be bluish white. Yeah, Tyler.
Is that where the idea of twinkling stars comes from?
No, the twinkling stars is because there's a bunch of stuff between you and the atmosphere. Or there's a bunch of atmosphere between you and the sky. So the twinkling comes from the light going boing, 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 through the atmosphere. But every star out there is whitish. Unfortunately, somewhere along the line, the people who wrote up your textbooks when they had color, 1960s, they said, you know what? We should make stars that are cold red. We should make stars that are hot blue. And it stuck. Even in current textbooks, you could look at the physics textbook we have, written in 2002. It still shows hot stars as blue and cold stars as red. The fact of the matter is, every single star that uses nuclear fusion releases all of the spectrum. So they would all look white. Unless the spike is so significant that it looks reddish enough to be like, oh, it's pink. Or it looks bluish enough, oh, it's turquoise. But for the most part, every single star, white. If you asked a computer who can see all wavelengths of light the same, what color our star would be, our sun, guess what color it would be? Green. We have a spike at yellow-green in our sun. But if you look at it, because we see all wavelengths of light squished together, they don't separate like a computer does, white. All right, questions? I think that is it. Yep. Okay. This is kind of fun. The sensor in your camera. It used to be this. This used to be this big. The sensor in your camera works exactly like your eye does. You have chemicals in your eye, and those chemicals are trapped in these things called cones or rods. I get them mixed up all the time. It doesn't matter. Anyway, let's just say they're rods. And those chemicals react to red, green, and blue. The camera in your phone does the same thing. It reacts to red, green, and blue. And then the material absorbs white light with the photoelectric effect. Some red gets absorbed, red electron goes out, and it goes to the red detector. Some blue gets absorbed, blue electron goes out, goes to the blue electron detector. Green comes in, green electron goes out, goes to the green detector. Then the computer takes all those numbers and paints a picture and puts it on your phone. Then you can upload it to Instagram. Your eye does exactly the same thing. Only we have chemical receptors that, well, pretty much work the same thing. Light comes in, they do a little chemical reaction, energy goes out, your nerve catches it and says, oh, that amount of energy is due to a blue photon. That lower amount of energy is due to a red photon. That middle amount of energy is due to a green photon. And your brain puts it together and says, oh, that's a classroom. Okay, I'm done. Questions before I sit down? All right. Yeah, let's click here. I'm pretty sure got through everything. Yep, all right, cool. And I can just close this. Instagram.